Actually, it seemed to me that whenever the sunshine came, I feel like it is Spencer Day. So because it is Spencer Day, I'm going to talking about the Spencer topic. So what is our Spencer topic today? Our Spencer topic today will be about the volume of solid revolution. Now I found this is fascinating topic. Back in 20 years ago, I was learning university when I haven't seen any of the 3D dimensional mathematical software generate the volume. And I remember our professor didn't show us anything. So I believe that with the new advanced technology now, with online internet learning, you should feel this topic a lot more interesting than me if you learn calculus, of course. Anyway, let me talk about the what we are doing today. So, sorry, let me get the pen. Okay. So on the board, I have the diagram, right? And you can see that the question of this, I didn't write down, but the question like this, find the volume of the solid object that is generated along the x-axis from 0 to 2 under the curve y equal to x. So basically that's the question, right? So on the board I have the linear I draw, which is the curve they given to us, and the equation is y equal to x. And we're going to generate this, revolving this along the x-axis, and we're going to use this method to solve this problem. Now, why do we corner this method? So this is the concept. I have to explain it to you, right? So I have a perfume on my hand. Now, remember the video I was talking about this topic, that in our real life, there is many weird objects. We could not find the geometric formula to solve for it. Unlike in high school, we already know how to use geometric formula to solve the volume of the hexagonal prism or the square base, pyramid, whatever. But in our real life, actually, there are some weird objects we don't have a geometric formula. And therefore, calculus came from to allow us to use our imagination and conceptual thinking in mathematics to perform our tasks. Now, when I show you, this is just the symbol of film bottom. I hold it in my hand, but outside the object could be the building. The object could be the weird shape of the ceiling of the church, or it could be some model we want to build in the playground, in the park for the kids or something, right? And therefore, to do those things, we need the science of engineer and architect to add into it. But everything came from a symbol calculation, which is we call it calculus. And actually we call it symbol, but sometimes the computation is not as simple as this. But let's take a look at just the symbol object now. Pretend we have to build a model of this, right? So this is the bottom. And I'm going to show you closer so you can see. If you just imagine that we don't have a body of this volume, right? We haven't generated, we don't have a body. It's just the curve on the top. And if you see the curve on the top from here, bending in here, indent here, and then go high a little bit and go slope, slightly go down like a linear straight line, right? So this is the curve of the object we are using here. Basically, this curve here represents a function, right? And it's not a linear function. A part of it is linear, but down here is indented and bending it, right? So this is the curve. Now, our task is we have to generate to revolving around the x-axis to find the volume of this bottle. Now, what we do is we use this method, right? So according to this method in calculus, we're going to slide this object into very small cross-sectional area. And each cross-sectional area have a shape of a disc, and that's why we call it this method, which is a circle, right? So we slide it in a circle shape. And derivative is we slide them into a very thin strip, or in this case, 3 dimension. We did thin rectangular shape under the region, right, area. Now we're talking about the volume, which is each strip here will be a cross-sectional area of a circle. So derivative is how the function itself is the area, the derivative of the area under the curve, which is the function itself, right? And then derivative, we chop them up into small pieces, slices, and integration mean antiderivative, the process go backward, right? So instead of chopping them down as the derivative, now we integrate, we put these slices together to form an atom volume under this curve, okay? So that's the idea of integration. It means we add on the cross-sectional total area together from 0 to 2. From 0 to 2, okay? So let's see how we're gonna do it. So let's talking about the formula of the volume of the object in general. In general, if you have any formula, any object, the general formula to find the volume is 3 dimension. It means we find the base area and we time with the height. If you stand up, it's the height. If you lie down, it's the length, right, of the object to find the three-dimensional volume. So in the cylinder, this base is a circle. But in the square base pyramid, is the square at the bottom, right? So the general formula is always the base area times with the height to form a 3-dimensional figure. So the base here is a circle of the disc, right? So I'm going to write out the general formula. Volume equal cross-sectional area, cross-section, right? Time with the height. And the height is the length of the object, right? So imagine this curve like that. And let's say you generate like this. So this is the length of the object, right? From here, all the way from here to here. It's the length of object. So our cross section is this, and it's a circle, which is the area, and I call the area of cross section, right? And the area of this cross section is the base area is a circle. So the formula to find the circle area is pi r squared times with the height. But remember, this is not the fixed number, right? Any formula here stands for something changing, and that's we call a rate of change. Our height, when we slide it, right, into small disc, the height of our object from here to here, if we stand this bottom up, right? This is the height and this is the length, right? Let's call the length so that you don't feel so much difference. So let's say the length, okay? So the length. So this length, the length here was divided by the many cross-sectional discs, right? So each slide here, when I slide it, have a delta x, the width of each slide, right? The thickness of each slide here is the width of the whole length here. And the width of the whole length here is, we call delta x, which is we use the endpoint coordinate, subtract this coordinate. We got the width from here to here. Now each slide we slide equally, right? So each width here, each delta x here is equally. And the delta x here actually equal the whole length from here to here, right? From here to here, the whole length from here to here, divided by the end strip and cross section, this, right? So the delta x here equal 2 divided by n actually, right? So now you get it, right? So I'm going to say, okay, so how we do this solution? First step, we'll subdivide the volume or the object into cross-sectional shape of a disc, right? That's the first step we do. So second step, we will find delta x. And delta x equal 2 over n. Okay? So now I'm going to write down delta x is 2 over n. So our volume is pi r square, which is the cross-sectional area, times with delta x. And delta x is the width of the disc is 2 over n, right? But also remember this r here is not a fixed radius, right? This r here is the radius of a disc. And the radius of this is changing from bigger, from smaller to bigger, right? And it changing under the curve. So whatever the curve here, the radius will shaped by the curve. So therefore, this radius here is no longer a fixed radius we can substitute in, but we have to substitute by the radius of the function, right? This radius actually is the height length of the function, which is the y-coordinate. So if our height is here, this is y1. If our height here, this is y2. So the y-coordinate here changing according to the function. So now we have to substitute the radius by the function. So this will be v equal pi times with f of x and square it like a formula, find the area of cross section, times with 2n over n, or just delta x. Let me put this in here, delta x. And then we substitute delta x by 2 over n, sorry. 2 over n. Oh, what I'm doing, 2 over n, okay? So now we have the volume. But remember, this volume is just one cross-section area, right? We're not talking about adding them together yet. We haven't iterated yet. We're just talking about the formula, okay, of one cross-sectional area. Now, also, we have to know that the y here is not a fixed y, or the x here is not a fixed x. It's according to the x-coordinate and the y-coordinate. And the x-coordinate here is changing, right? Change position. So in here, the x here is 2 over n, which is the whole length here divided by n strip, right? 2 over n times with, I can't say x1, so time with, or I can't say I1, and then another section is I2, I3, I4, I5, so on. So the coordinate of each x here, and we use the right endpoint coordinate, will be equal to 2 over n, which is the length of the width, times with the first coordinate here is I1. The next one will be 2 times with I2 over n. The next one will be 2 times with I3 over n. So that is the x-coordinate of this width, right? The x-coordinate of the strip of the width, the length of the thickness of the disc. So I'm going to substitute the x here But before we do that, let's substitute the function first, right? So what is our fx function? Our fx function is y equal to x, right? You see fx equal to x. So I'm going to substitute fx by 2x first. Square it times 2 over n. Now I also substitute x by the x coordinate, each x coordinate here from the right end point, right? So volume will be pi times with 2 times with the x. And each x here, so the first coordinate, x will be 2i over n. The second will be 2i 2 over n, 2i3 over n, so on. So 2i over n, okay? So I substitute the x here by 2i over n. That's the x coordinate. Because none of them are a fixed number, right? They aren't changed. The x coordinate here changing, the y coordinate change from y1 to y2, y3, and so on, right? All of this will be square times with 2 over n. So turn out the volume of one cross-sectional area is pi times with 2 become 4, 2 square times 4, I square over n, times what 2 over n. So this will be simplified one more. 4 times 4, 16, 16 times 2 is 32, I square, and we have a pi, so let's put the pi in. All of this over n squared times n is n to the power 3, right? So that's our volume. But remember, this is just one cross-sectional area. Now, to find the volume, we have to add on of this slices of this here, right? Each this here have to put them together. And to find the total area of to find total volume of on the fractional area, right? And total, whatever, anytime we call total, it means the sum. And the sum mean the sigma notation, right? So I'm going to write down, I think it's the light is dark a little bit, right? Because light. Okay, so I'm going to say this. I will say this is, now we're going to find total, right? And total means sum of all of this cross-sectional together. And sum means sigma notation. So I'm going to use the Riemann sum in this method first. Riemann sum combined with this method, okay, to solve this problem. So on top is n, and down here is I equal 1. And to find the sum of this, because we divide n is so many small cross-sectional, right? So many slices. So when we add them, we're trying to do it in a way that less error. And the only way we can find the volume less error is when we cut them to the small slide, make sure we cut so many slides, thin strip, right? And therefore we let the n go to infinity. The n become a huge number, right? Let n go to infinity, and we take the limit of it. So our volume actually will become, so therefore volume will be equal limit when n approach to infinity of the sigma notation 32 pi when n approach to infinity and I equal 1. I square over n to the power 3. Okay, so when we make the n go to infinity and take the limit of the sum of on a cross-sectional area, we will find the volume like this, okay? Now, in order to calculate this volume, I have to do a little bit with sigma notation. So I'm going to bring out whatever here outside. And inside, I just left with I square. All of them I can put outside. Remember, that's the way the rules in sigma notation, right? So we can bring them outside, and remember, we're still talking about limit of it, n approach to infinity, right? So 32 pi, and n3 can come out as well, and about 3. Inside will be, let's just put n on top and I 1, and will be I squared. Now all of this outside multiply with the total of the sum of the square number, right? So remember, back into those previous video, and that's why, here you go, I have a chance to advertise for my course. If you register to my course, you will be able to connect these ideas together. Rather than watching from YouTube or watching, you can go to my mathteaching.ca to learn the weekly lesson I post as well. So far, I have posted a couple of them in the calculus course. So you're welcome to visit my website, which is my mathteaching.ca. Okay. So now let me talk about how we calculate the sum of the sigma notation of I squared. Remember, back in those days, I have proven to you this formula, right? And so for today, to calculate the total sum of these I squared, we just use the right-hand side of the formula here to substitute for our calculation. And that's why math is easy, because we have proven the formula, now we use the formula, right? So I have proved to you that the I square here, the sum of the square of the natural number, it just equals the right-hand side formula here, right? So now I'm going to use this, substitute into our calculation, and solve for it. And I don't bother to prove it again. It takes me another hour to prove it, right? So now, and you see that math is a related concept, right? Okay, so now I'm going to change this, become the formula, right? So the whole thing here will be substituted by the formula, which is n times with n plus 1 times with 2n plus 1, that's the right-hand side of the equation, divided by 6. So now our task is calculate this volume. So 32 pi over n to the power 3 multiply with, now I'm going to cancel the n up top here, right? Let's write it again. We'll cancel this n with this n down here. So that becomes n squared, right? All of this divided by 6. So volume equal 32 pi. I'm going to multiply through. So I got 2n squared, this time this, adding with n, adding with 2n is 3n, adding with 1, divided by 6, right? And don't forget, we still have a limit of n approach to infinity. And this still over n squared. So now I'm going to, because I want to cancel n squared with n squared down here, so I'm going to factor out the n squared, okay? So 32 pi over n squared. I'm going to factor out the n squared, so inside I have 2, adding with 3n over n squared, adding 1 over n squared. And we're still talking about limit when n approach to infinity. So at this point, I can cancel this with this, right? Now remember the concept of limit. If you have a small number on top, divide by a big number at the bottom, so this will be get closer and closer to 0. So consider this will be equal to 0, and this, when n approach to infinity, this number will become 0 as well. So now we're left with, what do we have here? And don't forget, we still have to divide by 6. Yeah. So now we'll continue here. I have no room. So now I continue here. Our volume will become 32 pi times with 2 over 6, right? Because all of this term becomes 0. So we left with 2 over 6, which is the same like 32 pi over 3, because I divide this by 2 divided by 2. So 32 pi over 3 cubic unit. That's the volume. So that is our answer. Okay. Now, before I go to the next question, I'm going to summarize a little bit the idea for you, okay? So we are going to do the volume. We're going to generate the volume of solid revolution and revolving around the acid, right? I don't know why it looks so dark. I could not see my audience. Okay, so now, sorry about that. Okay, I think it's become affected by the sun outside. So I adjust the screen a little bit. Okay, so we generate the volume by divide the region into so many slides, and each slide have a shape of a disc. That's why we call it this method, right? And we generate from 0 to 2, so we know that this 2 unit will divide by n slides or n discs, right? And the thickness of the disc is equal to 2 divided by n time, and we call that is the delta x, which is the thickness of the disc or the width of the disc here. It turned out the whole length here is the height of the volume if we stand this cone up, right? So the length here is the height of it, and volume equal pi r squared, the area of cross section, time with the height of it from here to here. But because none of them are the fixed number, so when we talking about volume equal pi r squared time with the length, we substitute this by f of x, and we square it according to our formula. We substitute this by delta x, because that's the thickness of each disc here. And the x coordinate here also have to substitute by the right end point, which is 2i over n. So our function is 2x. First, we substitute the fx by our function, right? Time with delta x, we know that 2 divided by n, we substitute in. Now, this x is the x coordinate. The x coordinate here changing by x slide as well. So we just pick up one right end point of the x coordinate, which is the whole length is 2 over n. We time with the first one is I1, second one is I2. But let's just pick one symbol here. You substitute this x by 2i over n. That is our coordinate. All of this will be square times with 2 over n. And then after we're done, we find the limit when n approaches to infinity, and we add the total of all of this line, put it down here together. We call it sigma notation. And then we use the formula of it for the sum of the natural square. We use that formula, we multiply with this, and we come up with the answer like that. Okay, so I hope you enjoyed this question and my video today. I will continue with the next question In this question, I use the Riemann sum, so it's a kind of complicated and long way to do, but we learn the concept along with it, right? The next question I will show you using the integration technique in calculus instead of Riemann sum, and it looked very easy. It's a lot easier than this method and shorter, okay? So I have to erase. So after our first example, and we calculate the volume of solid revolution using this method and the sigma notation. Now we record the formula. So the volume will be equal the total area of the n slide, right? When this n go to infinity, and the formula for the cross-sectional area is pi r square, but our r beyond shaping, like our r was shaped by the function. So in this way, it will shape under the linear. In this way, it will shape under the cubic function. So therefore, it will be based on this is r, right? This is r, pi r and square. Time with the thickness of the dish from here to here is delta x. So that is the volume. And we take the limit. So volume equal limit of this sigma notation when n approach to infinity. Based on this formula, we will develop it under the integration technique. So now we will say, instead of doing cutting like using the Riemann sum, we'll say we're going to develop by integration of the cross-sectional area from A to B, right? And it will be equal pi f of x square dx. And dx here stand for the delta x here, because we already take in account of the thickness of the delta x by the length from the region, from the length, the interval from A to B, right? From A to B. From A to B, or from here, it's from A to B. So therefore, this is the formula. So now, we're going to use this formula. So now we say from now on, therefore, the volume under this method, which is the cross-sectional area is pi r square, and our r turned out to be the function f of x delta dx. Or you can say AB pi. Now I like to use the f of x, but you also can use y square dx, right? Okay, so let's get into using this formula now. We're going to generate or find the volume of this cubic function. So let's say given the cubic function. Now, everybody know the cubic function in this shape, right? Y power 3, right? In this shape. So this is the cubic function. Ask us to generate the volume of the solid object from 1 to 2 under the y function, y equal m of x to the power 3. So we now, instead of using the sum of Riemann sum, it's more complicated. We're going to apply this technique in here. So we're going to generate the volume from 1 to 2. And our equation is, this is the same like y equal x to the power 3, right? So we're going to say this is the y function equal pi r squared to x power 3 squared dx. So to find the volume of this solid area underneath the region when we revolving around the axis, we just slide this area into the cross-sectional slide and we generate it, right? Revolving, we get this shape. Okay, so I'm going to use it here and say volume will be equal over pi, we just bring it outside, and this it become x to power 6, right? X to power 6 dx. So that will give us pi divided by 7, x to power 7. We're going to generate from 1 to 2. So that volume will be equal pi over 7 x. We substitute the x by 2, right? 2 and power 7 minus pi over 7, and the x is just 1. So it times with 1, but 1 power 7 is just 1. So that's okay. Now what do we get? 2 to power 7, I believe is 128, but let me check to make sure. Okay. So 2 to power 7, yes, 100. So 128 pi minus 1 pi, so, and because they have the same common denominator, so it turned out 127 pi over 7. That is the volume, square unit. Square unit. The answer is the volume is 127 pi divided by 7 cubic units. So this is our answer. Let me summarize a little bit about what we've been doing so far, because this question are complicated. So the first question, we have a linear, and there is a region underneath this linear. So we're going to generate the area, the region underneath this linear, revolving around the axis to generate the shape of the volume of this object. And we use the length of from 0 to 2 unit. We divide into each slide like this. But each slide here is the 3D object with the shape of a dish, not just the area, 2 dimension, but it's 3 dimension, right? Each shape here is the shape of a disc. So each disc here have a width, a thickness from here to here, a thickness from here to here. And I draw it as an extreme rectangle with the thickness of delta x, like that. So we know that if we generate from here to here, then how many slides we divide, that is the same how many thickness we have, which is equal to divided by the n slide here. And the thickness of this each delta x here equal to 2 over n. Now for the coordinate, we know this is I1, this is I2, I3, and I4, and so on. Each x coordinate is the length here, 2 times I divided by n. So we know each coordinate here represented by the end point of the coordinate x here, 2I over n. Now, when we use a Riemann sum, we add this line together, and that we call an iteration, so that we can find the volume of the whole thing. So when we add them, we also realize that the volume of this is have a cross-sectional area of a dish multiplied with the height of the volume or the length of the volume. And the length of the volume is from here to here. The base radius of each slide here is R3 here, R2 here, R1 here. And this R, the way we find this R, we base on the function, because to find the coordinate Y of each coordinate X, we have to substitute the X here and follow the function and find out the length from here to here, the length from here to here. And this length is keep changing. And therefore, we substitute this R not by a fixed number, but by the whole function. And we follow this formula, we square it. So this is the formula in Riemann sum. From this formula, we derive this iteration. So from now on, our task will be a lot easier if we use this iteration. We generate the volume from A to B, which is A here, B here, and we follow the formula of the cross-sectional area multiplied with delta X. Now, the delta X is mean the length from A to B here, which is already taken care in this formula. So we derive at this formula. Now we use this formula, we solve the next question. And we get the answer is 127 pi over 7 in cubic units. So that is very much about the lesson we learned today. I hope you enjoy it, and thanks for watching. Stay tuned for our next lesson.